Okay, let us continue our discussion of psychrometry. This is part 1 of module 6. So here we'll continue our discussion of the moist air model, specifically the psychrometric chart, how we can express properties of moist air through this chart. We'll develop mass and energy equation, which is discussed in section 12.2 in your textbook, and along that line we'll discuss psychometric processes. We'll have a separate module where we'll solve some problems with these concepts we are going to discuss now. So let's start with the psychrometric chart. Well, essentially we discussed in the last class the x-axis has the temperature, which is also known as the dry bulb temperature expressed in Celsius. And what dry bulb temperature in psychrometry means that the bulb of the thermometer must be dry as opposed to wet. If it is wet, it will read a different temperature, which is known as the wet bulb temperature. So x-axis is the dry bulb temperature, which is our day-to-day temperature as we understand, temperature of the air. But remember, in the psychrometric chart, any point here represents, suppose a state 1, represent the state of air, the vapor in air, in moist air. Of course, the temperature is the same thing as temperature of air or vapor. They share the temperature, as we know. On the y-axis, we know it is vapor pressure of the air, or omega, because they are 1-to-1. Omega, which is what? Mass of vapor divided by mass of air, is a function of vapor pressure. In other words, if you know omega, you can find PV. If you know PV, you can find omega. They're 1-to-1. Also, we know that the relative humidity, phi, is given by vapor pressure by maximum vapor pressure, which is also known as Pg. It has many different names, or set at T. We discussed that in our last module. So when phi equals 1, which is this line, phi is 100%, let me pick a different color. So when phi equals 1 for 100%, oops. Sorry about that. Okay, when phi is 100%, we know the vapor pressure would be maximum. So in other words, this is PV max. From this chart we can find, and this is PV. And their ratio is relative humidity, shown by state 1. So let's quickly run a thought experiment to find some new properties. Okay, let's say we have a tube where air enters at state 1, that's 40% relative humidity. I don't know, you can see it here in this number. This is about phi equal 0.4. So moist air is entering, and suppose we are heating it with a candle, this air. Somehow we are heating it, doesn't matter how. And we'd like to know how to spot state 2. Well, it's common sense that temperature will increase. Anybody will agree that I'm heating the air, therefore T2 will be higher than T1. So we know we'll move to the right. The question is, will you move up or down? Well, I would like you to stop the video right here and think about it for a second. And come back. Okay, assuming you listen to me, tell me, would you think that the air will be drier? Everybody will realize we are heating the moist air will feel dry. So many will think that, oh, well, that means probably the vapor pressure is going to be lower. Or some people will say, wait a minute, pressure generally goes up if I heat, but maybe vapor pressure is higher. If you think of vapor pressure, you're in the wrong track. It's very difficult to figure out thinking of vapor pressure. Instead, think in terms of omega, and then you will see the answer immediately. So what does omega mean? Omega means mass of vapor divided by mass of air in any any lump of air. So if you take any lump of air, so suppose in your mind you just choose a lump of air here, and let's say we are representing the air molecule by blue dot and the vapor molecule by red dot. My question is, as this lump of air passes through and gets hotter, do you think the number of red dots are going to grow or number of blue dots are going to grow? No. The number of molecules are not changing. We're just heating them, so maybe the lump is going to get bigger. So when it comes out, it is possible, as a matter of fact, this will happen. When it comes out, if I draw this, after heating, this lump will get bigger, and now we'll have exactly same number of molecules as before. So the omega hasn't changed. Another way to look at it is that omega is also m dot v by m dot a, right? In every second how much vapor is going in, every second how much air is going in, the ratio is omega. So that's omega 1 here and omega 2 here. The question is omega 1 and omega 2 any different? The answer is an absolute no. Now think about it. I'm heating the gas, but the amount of vapor that enters here every second must be the same as amount of vapor coming out if the system is at steady state. So at steady state, omega is not changing. So therefore, if omega doesn't change, the state will move to the right, and maybe, suppose we know the final temperature, this will be my state 2. As you can see, the relative humidity here, this is phi equals 30%. And over here phi was 40%. So yes, the relative humidity decreases, and we call it drier air because our skin responds to relative humidity, not vapor pressure. But as you can see, the vapor pressure or omega doesn't change at all. So it becomes complicated because see PV, so therefore you can see that PV doesn't change, but P set is changing. We know as temperature increases, the PV max is increasing, so P set, the denominator, is increasing, but PV doesn't change. Therefore, phi keeps on decreasing as you heat the air. On the other hand, suppose we are cooling the air. So let's start again from the same initial state. Suppose we have state 1 here, and this time we are cooling the air. Again, as long as there is no condensation, would you agree that temperature will be decreasing? So we are taking heat out. Q dot out. So as long as there is no condensation, omega doesn't change because the ratio of omega 1 So therefore, we keep moving to the left horizontally. Omega doesn't change until the air becomes saturated. So once the air is saturated, that's a relative humidity is 100%. What happens now? If I cool any further down, then obviously the state of vapor cannot go any further to the left because the air is already saturated. So the only way to go, the air will remain saturated. So if I keep cooling, suppose at this point the state became saturated. And if I keep cooling this air, at state 3, it's so cold, so that I force the temperature to go down. Maybe this is state 3. So this is how the process will look like. But if the final state is here at state 3, notice this is my omega. Omega 3 is much So omega 1 and omega 2 are equal, but omega 3 is much less than omega 1. So what does it mean? notice that if omega 3 is reduced, that means mass of vapor must be less, because omega 1 is what? M dot vapor at 1, M dot air at 1. And what is omega 3? M dot vapor at 3, M dot air at 3. But M dot air is not changing as I cool the air. So A3 and A1 are equal, but omega has gone down, as you can see from the psychrometric chart. So therefore, some water must be coming out from here. Air must be losing some water. And that is because omega is decreasing. And that is known as dehumidification of air. Again, when we solve some problem, this will become more clear. But the reason I'm discussing this is because state 2 is very special. This way of saturating air, when the vapor pressure doesn't change, then the temperature at which the air gets saturated, which can be found from this chart, is known as the dew point temperature, TDP. So what is the dew point temperature? If you take some air at anywhere here, moist air in this chart, and horizontally move to the left, when the air becomes saturated, the temperature is known as dew point temperature. Very simple. So now we know another property. If you go to the psychrometric chart, I already put that here for you. In this particular animation, you can see that how the chart is built. So let's start with, for example, understanding the axis. You can see how the pressure versus temperature diagram. Pressure is moved to the right, and the temperature is called the dry bulb temperature. And of course, this big blue line, the fat blue line, is the saturation line. This is the phase diagram of water, essentially telling you the boiling temperature T for a given pressure. So at 30 degrees Celsius, for instance, at what pressure water boils. That's how we draw the blue line from the saturation table of H2O. And then we move this pressure axis, we just move to the right. And then we recognize, if you go to the omega is a function of PV. We discussed that in module 1. So omega, which is a ratio of vapor and air, can be shown as a function of vapor pressure alone. P is the total pressure, which is always a constant. So therefore, the line of constant omega or the line of constant vapor pressure are same. As a matter of fact, as you can see, even the dew point along this line doesn't change, because no matter where you are, think about it, when you hit this point, the dew point in this particular case is 13.8 degrees Celsius. So these are all line of constant dew point. So sometimes the dew point is also written on the y-axis. So the y-axis not only doubles as PV line or omega line. In psychrometric chart, you will find dew point is also in another scale given here, because along this line dew point doesn't change. Of course, we have already discussed the relative humidity lines. If you go to this button, relative humidity simply means when the vapor pressure is a certain fraction of the maximum pressure, and 40%. In this particular example, we are showing what is a 40% relative humidity lines looks. If you take the 100% line and find the 40% of that vapor pressure, all these points together will make the constant relative humidity line. We have already covered the specific volume line in module 0. They are sloped, negatively sloped, as shown here. Again, it comes right out of the formula. If you write the specific volume, which is defined as the volume per mass of dry air, per unit mass of dry air, using the ideal gas equation for the perfect gas, for the dry air, we end up with a formula that shows that specific volume must have a negative slope. Finally, even though we haven't, okay, we'll come back to the enthalpy line after we cover enthalpy. Okay, so let's go back to the PowerPoint now. And this time we want to build up the mass equation first. In other words, what would be the steady mass equation look like for psychrometric processes? So suppose we have a moist air flow going through a tube, and let's say many different things are happening. Water can be injected, water can be taken out. It's best to describe this through an animation. So I'll go straight to, let's find, let's see where it is. Oh, right here. Okay. So let's pause the animation if possible. Okay, so as you can see, we have moist air going in here at state 1 and coming out at state 2. And a lot of things are happening. Obviously, in a given problem, only one or two of this could happen. There is water injection at state 3 to humidify. That's called humidification of air. There is a cooling coil, which means basically heat is being taken out. Q dot is negative. That is, Q dot out is going on. A coolant is supplied, maybe chilled water to this tube. As a result, heat is taken out. We'll not consider that as mass coming in, mass going out. We'll just assume some heat is being taken out. As a result, it's possible the temperature may go down below the dew point temperature. We know if the temperature goes below dew point temperature, dew appears. And as you can see, the water is being collected, the condensate is taken out at state 5. That's called dehumidification, because you're dehumidifying the air. You're taking humidity out of air. Over here, we're injecting steam. Again, this is another kind of humidification, but when you inject steam as opposed to water, steam not only humidifies the air, also it heats the air. So it's heating with humidification. Finally here, we can see there is some heating coil. Basically, electrical work is put in, essentially energy is put in here to heat up the air, and finally the air is living at state 2. The question is, how can we satisfy mass and energy equation for such a complicated system? Turns out it's really simple. Think of mass equation first, and as you can understand immediately, if you just want to talk about air of mass of dry air, so air, in fact moist air, whenever we talk about mass conservation, we separate that into dry air and water vapor conservation. Obviously, dry air is conserved in this problem. Whatever dry air enters must be going out, because notice this water injection doesn't affect the dry air, heat transfer doesn't affect the dry air, steam injection or heating coil, none of them affect the dry air flow. So to understand dry air flow, we can get rid of all this extraneous stuff, and it boils down to dry air is entering at state 1, going out at state 2. And what can you say about the mass of dry air going in and coming out? They must be equal, right? So therefore, it simply boils down to that we can just represent that there is only one mass flow rate of air given by m dot a. Nothing else is present in this case. So there is only one unknown m dot a, and that tells you why all the units are per kg of dry air, if you noticed. Okay, now if you go to the water vapor, what can we say? If you want to see the water vapor, H2O flow, notice that you have to think of how much H2O is entering. We know the vapor that is entering is given by m dot a times omega 1. Omega is the ratio of vapor to dry air, right? So therefore, the balance become what goes in are all shown here. M dot V1 is the vapor that is entering. M dot W3 means water that enters at state 3, water that enters at state 4. These are all on the left hand side. And on the right hand side, we have the vapor that is exiting at state 2 and water that's exiting at state 5. Now, why do we have two different subscript V and W for H2O? Well, V means vapor in moist air. So m dot, any V subscript will emit it, like PV is the vapor pressure. M dot V is the vapor that is part of moist air. Whereas W means H2O, but it's pure flow of water. So if you simplify this equation, you notice that the vapor flow can be expressed in terms of dry air flow times omega. So that is the clue in connecting vapor mass with dry air mass. So whenever you see vapor mass, you can just multiply the dry air mass with omega and get the vapor mass. And dot simply means per second basis. So if air is entering, moist air is entering, say your house at so many kg per second of dry air mass flow rate, then you multiply by the omega and you know how much vapor is entering. So therefore, here also you can very quickly convert the vapor that is entering in terms of dry air that is entering times omega. Similarly, you can see the vapor that is going out with the moist air is given by this term. And by little manipulation, the equation becomes very simple. So in other words, from now on, whenever you see moist air entering somewhere or leaving somewhere, you have to think in terms of there is some dry air and water vapor. How much dry air is entering, and multiply that by omega, and you'll know how much vapor is entering. So therefore, constructing a balance for H2O is keeping track of all the vapor that enters and exits out of a system, and the direct injection of liquid water or direct removal of liquid water through condensate or steam injection. These are different ways in which the water amount can be affected. Okay, so now let's look at the energy balance. Well, first of all, to understand the energy transported by moist air, you have to think like, well, whenever moist air is flowing, it has two components. One is it has vapor that is flowing, and another is dry air. So you can see the enthalpy carried, the flow energy carried by a flow of moist air. If you sum them up, the energy carried by dry air and vapor, it's very simple to understand. But then this becomes complicated to evaluate. Think about it. Then you have to keep track of enthalpy of dry air, enthalpy of water vapor. So for vapor, you have to run to the steam table, and for dry air, you have to use the PG model, MCP delta T, etc. CP delta T to get the enthalpy difference. So it becomes very difficult to calculate the enthalpy of moist air. Here comes a very simple helper. See, if you take m dot A out, and then it becomes HA plus m dot V over m dot A, which is omega. So this quantity, if you notice, you can, HA is finding the enthalpy of dry air, and HV can be calculated from, looked up from steam table. So therefore, in a psychrometric chart, suppose I have a psychrometric chart, and for any given state, we know the temperature. Therefore, we can find HA, because HA is what? Function of temperature, right? For dry air. And HV, we can find also from, it's a function of pressure and temperature, right? To find vapor enthalpy. But because the state is known, we can find vapor pressure from this axis. And if we know the vapor pressure and temperature, we can find enthalpy of vapor. So in other words, for a given state in the psychrometric chart, we can calculate this quantity and tabulate that. And that's called enthalpy of moist air per unit mass of dry air. So because you have to multiply by the mass of dry air mass flow rate of dry air of this new quantity, new enthalpy of which is given by enthalpy of air plus omega enthalpy of vapor. So this is a new quantity, and its unit you can see will be kilojoule per kg of dry air. So therefore, if we can tabulate that enthalpy in terms of that new moist air enthalpy, the energy equation can be now rewritten. So the standard energy equation is what? Energy carried by flow, which is this one, flow energy transported by the moist air, made up of air, dry air. Sorry, this is the energy transported by, I'm sorry, I misspoke. So let me just redo the energy equation again. Notice the energy transported by moist air now is given by this quantity, where we'll just keep track of dry air that is coming and the enthalpy that's in the psychrometric chart. And then the enthalpy that is carried, this is from the water injection. If I know the mass flow rate of water, and if you can find enthalpy of water from the steam table, from the saturation table, then we know the water enthalpy. This is what? This is the enthalpy of steam coming in, steam's enthalpy. So these are all the energy carried by the flow, and this is the heat added by heat transfer, energy added by heat transfer. This is energy carried out by moist air at the exit at state 2. Notice that m dot A is the same. And this is the energy that is leaving by the water that is leaving as condensate. And this is if any work is leaving, of course. In an air conditioning process, work is added, so it will be negative. So in other words, if you go physically, try to understand this equation, read the book, and you will see, you can understand it physically. What it comes down to, you keep track of energy, and to find the enthalpy of moist air, we can go back to the psychrometric chart that we just covered, and you can see the enthalpy is already listed on an axis like this. We can, because of lack of time, you can go and show that if you just follow this equation here, you can show that the slope will be negative, just like specific volume. So if you know a given state, you can go and read off the enthalpy from this chart. Just for the sake of completeness, let me show the actual chart, how it looks like. It looks very similar in its psychrometric chart, table F1. And here, this is the enthalpy as we talked about, if you recall. I would suggest you print out this or copy from your textbook this psychrometric chart, and when you solve the problem, use this generously so that you can draw on it with a ruler. You can follow something, and just to highlight, I know in this video it will not be probably very clear, but again, this is the dry bulb temperature. Here we have vapor pressure, we have omega on this axis, and this is enthalpy, as I already talked about. And specific volume lines are a little bit difficult to see. These are the specific volume line. Anyways, so take a close look, print it out, and see if you can track different properties for a given state. So if you know a state, you should be able to quickly spot it. Suppose a temperature and relative humidity is given, let's say relative humidity is given to be 50% and temperature is 30 degrees. So you'll follow the 30 degree Celsius line until it hits the 50% relative humidity line somewhere here. What would be then, for instance, omega? Then we'll come here to pick up omega, which is about 21. If someone says, what is the enthalpy? Then we'll follow this line and we'll say it's 76 or 74, whatever. If someone says, what the dew point temperature? One way is to go here and go there and pick up the temperature. Also, we know that dew point temperature doesn't change along this line. No matter where the starting point, here or here, dew point temperature is the same. That's why here also the dew point temperature is listed. You can go and read off the y-axis. Well, I'll stop here and let me see. How about we'll stop right here and we'll try to solve a couple of problems with whatever we learned so far.